In the last clip, we introduced Huffman Coding, and in this clip, we will go step by step and see how the algo works. Let's start with adding all the elements from our frequency table to the priority queue, which is a count of all characters in our input string. You will notice that in our priority queue, the top MOT elements are the ones with the least occurrence in our input string. Now we pop two nodes from the queue. These two nodes will be the least occurring leaf nodes. We merge these together and create a new Huffman code with value 2, which is a sum of the two frequencies of the C node and the D node. We link the D node to the right and the C node to the left. In this case, we can choose either to be the left or right, but we will put the node with the lesser frequency to the left and the one with the greater to the right. You can use the opposite rule as well, but the rule should be the same for constructing the entire tree. Now we have a subtree that is formed, which we will add back to the priority queue. We continue merging nodes as long as the queue size is greater than 2. Currently we have 3 nodes in the queue, our newly created and added subtree, and the other two leaf nodes, B and A node. So now, once again, we pop two elements from our queue. This time 2 nodes, one which is the subtree node 2 and another leaf node B with value 2 are the 2 nodes that we will need merging. Now after the merge, we have created node 4 with the previous subtree as its left node and node B as its right node. The node 4 has the frequency of 4, which is the sum of the frequency of node 2 and node B. Now let's also add this new Huffman node 4, which is now a larger subtree back to the queue. You will notice that our Huffman tree is growing slowly. Our queue size is still greater than or equal to 2, so we pop the 2 nodes and merge gain. This time we add the value of node 4 and node A, which gives us the value 7. We add this new Huffman node back into the queue. One thing you will notice is that our tree is completely formed, since there are no more nodes in the priority queue, except for this one tree node 7. At this point we exit, and what we have is a Huffman tree. We pop the only element from the queue, and now we traverse this tree and assign a 0 to every left element and 1 to every right element. To generate the Huffman codes, we simply traverse the tree to every leaf node and append the binary value strings together. Now our Huffman code table looks like the following. The most occurring character has the least number of bits. A requires only 1 bit, which is 0. D, which is the least occurring character, requires 3 bits, and its bit code is 111. Finally, we use our generated codes to encode the input strings. What we land up with is 15 bits instead of 56 bits. This is a huge improvement. Even if we store the table for the codes along with the compressed text, on large files, this method can save a lot of space. Lastly, here is our decoding logic. This requires the Huffman codes table and the